So the next example is about finding the length of a circle. I mean, that's just a formula you already know. It's basically the circumference of a circle. That is 2 pi r, isn't it? But well, we're going to complicate it, make it harder than it actually is. But actually, well, not really. It's just we're going to take a different approach to obtain that result. Well, by the way, there's a little typo here. There's an extra t there that's not supposed to be there. Okay, it's just that. So what do we have? We have the parameterization of a circle in the plane. So we're gonna find its arc length, that is circumference. Okay. So what do we need? We need to find the derivative r of r prime of t, or the velocity function, if you will. That'll be the derivative of cosine, which is negative sine, negative r sine t, comma r cosine t. And I know what you might be thinking. Does the negative get absorbed with the constant r? No, not in this case, because since we're considering a circle, its radius is always positive, so it doesn't get absorbed like in other situations where we absorb signs with unknown constants, such like this, but not the case in this case. Well, the limit of integration, that is L equals to the integral of the square root of negative r sine t quantity squared plus r cosine t quantity squared dt. Well, what are going to be the limits of integration? Well, since this time we're considering a circular trajectory, and well, we want to find the length of the circle, not the arc length of a sector of a circle, say the first quadrant or the first two quadrants or the part in quadrant 3, for instance. No, it's the entire circle. That means 0 to 2 pi, right? Well, what's that going to be? Number 1, that's the integral from 0 to 2 pi of the square root of r squared sine squared t plus r squared cosine squared t dt. Alright, so actually we can factor out an r squared, that is r squared times sine squared t plus cosine squared t dt. And again, this identity, the Pythagorean identity, that equals to 1 times r squared, that's the integral from 0 to 2 pi of the square root of r squared. Well, I mean, technically, whenever we take the square root of a quantity squared, technically we should have absolute value bars, because we don't know what r is, if it's positive or negative. That times the integral from 0 to 2 pi dt. However, in this case, we don't need those absolute value bars. That's because, well, it's the radius of a circle. It's always positive, right? So we can simply call it r, all right? And then that's going to be equal to r t from 0 to 2 pi. That is r times 2 pi minus 0, which is 2 pi r. That is the formula you know for the circumference, isn't it? Yep. We're just taking a different approach. We're just using, this time we're using the arc length formula right here and a parameterization of a circle to get a different result, okay? All right, so here is where we're going to see this vector valued functions with a different variable. Well, that's because the easiest approach to handle this kind of functions, that means in terms of its variable, which is t. And well, we discussed this sometime during last week when we first discussed about vector valued functions, that these vector valued functions are formed by all these points at different values of t. And to make this easier to see, it's by considering the position of an object at different times, all right? So t is time. But it turns out that time is not the only parameter when it comes to parameterizing vector valued functions. Actually, another way to parameterize is by the arc length. For instance, well, this is what you know so far. So, see. Well, actually, how about okay. I can be in different positions at the same time depending on the path I choose, right? For instance, after 5 seconds, I can be here, or maybe after 5 seconds, I could be here. That is, if I have some function r1 of t versus a function r2 of t, different functions, right? So, but again, a different parameter could be this time the distance parameter, not the time parameter. Because what about the distance parameter? So if I am standing at a point like this point, I can move 5 meters in that direction or 5 meters in that direction, and I'm going to get to totally different spots, right? So it's in a similar way that at the same time I could be in two different places depending on the trajectory that describes my position or the position of an object. Same. Position after 5 meters, and then that's also position after 5 meters. But it depends on the direction you take. It depends on on how the trajectory is parameterized. Well, how do we get that new parameter? So we're going to obtain a new function, a function s that depends on t, where notice how it looks like the same arc length formula, but in this case we're making a change of variables. We're changing the t to a u to obtain a new function that is evaluated between a and t, where typically a is going to be 0 for the most part, and that's what we call the parameter, the arc length parameter. Let's have a look at one example and see how this works. Okay, so let's find the arc length function for the function r of t, that is s of t. So essentially, we are going to come up with an equivalent function that no longer no longer describes time, but rather describes a distance. So the position after 5 meters, after 10 meters, rather than the position after 5 seconds or 10 seconds, which is different parameter, different variable. How are we going to do this? Well, number one, change this given function, instead of r of t, make it r of u. That is u squared, 2u squared, and 4u squared. Okay? I mean, you can use the variable you want, but in this case we want u to go from u to t back again, or rather to s. Oh yeah, t technically. Okay, so here's the thing. Let's find the derivative with respect to u, r prime of u, that is 2u, 4u, 8u. Okay. So let's find the arc length function. How do we get this arc length function s, which represents a distance on arc length, and find the integral from 0 to t. Why am I starting at 0? Because of this condition. Here it could have been from -5 all the way to t, from 3 to t, but in this case, since we want it greater than or equal to 0, we start from 0. That's the most common case. So that'll be the square root of x prime of u squared plus y prime of u squared plus z prime of u squared du. That is the integral from 0 to t of the square root of 2u squared plus 4 u squared plus 8u squared du. So that's going to give us, okay, let's simplify this. The integral from 0 to t to s, that's the square root of 4u squared plus 16u squared plus 64u squared. And well, the good thing here, we have a bunch of like terms, and we will easily simplify this radical, unlike the one we did at the beginning of the section. All right, so let's see, 4 plus 16, that's 20, plus 64, that's 84. That's the integral of the square root of 84 u squared du from 0 to t. So in this case, the square root of u squared, that's just going to be u. And the square root of 84 could be simplified because it's a number divisible by 4. That's 21 times 4, which reduces to 2 square root of 21. But keep in mind that the u right here, it's outside of the radical, so careful. So that's just going to be a multiple constant. Let me take it outside of the integral. That'll be a lot easier. 2 root of 21. Integral of u du from 0 to t. So that'll be 2 root of 21, and that's u squared over 2 from 0 to t. These two, of course, are going to get canceled. That's going to leave us with the square root of 21 times t squared minus c squared minus 0 squared, which is s equals to the square root of 21 t squared. Okay? So what are we doing here? We're getting a new function, a function that relates s with t. We're going to use this this equation, if you will, to solve for the variable t and reparameterize our t's in terms of s. Okay? So how are we going to do that? Well, it could be a little tricky because, yes, if we solve for t squared first, that gives me s over the square root of 21. And then you might want, I know what you might be thinking, you want to take the square root of t, but that's going to give you plus or minus the square root of s over the square root of 21, this funky quantity. But, well, you don't need that. Actually, this is fine because, okay, check this out. That's because, what do we have? T squared, and t squared. So just substitute t squared with this quantity. So now we reparameterize. This is no longer going to be an r of t. This time, this will be an r of s. R of s, that equals this. So t squared, which is simply s over the square root of 21, 2 times s over the square root of 21, and 4 times s over the square root of 21. So that is our new function. So it's we're doing a change of variable on the parameter t, which represents time, and we're going to change the variable to a distance variable rather than time variable. Well, if this sounds or looks weird, well, it's going to make sense when we look at the definition and the condition for this to be an arc-length function. Well, first of all, what is the magnitude of r prime of s? I wonder why we would want to do this. Okay, so that's to connect the idea where we wrap up the section, by the way. All right, so let's find the derivative of this. That is r prime of s. That equals, okay, the derivative of s with respect s is just 1 times, well, the number it multiplies, which is 1 over the square root of 21, comma, the derivative of s is 1 times 2 over root of 21. That's root over root of 21. And lastly, the derivative of s times 4 over root of 21, that's just the coefficient 4 over the square root of 21. Okay, now they're asking us to find the magnitude of this vector. So, let's find magnitude of r prime of s. That equals the square root of 1 over the square root of 21 squared plus 2 over the square root of 21 squared plus 4 over the square root of 21 also squared. Yes, looks ugly, but it will simplify to something really nice. You'll see. Okay, so in the denominators, those square roots of 21 being squared, the square cancel the square root. Okay, so that's going to give us a bunch of denominator ones. All right, that's the square root. Okay, 1 squared, that is 1 over 21 plus 2 squared, which is 4 over radical cancel with the square, that's 21, and 4 squared, which is 16 over the square root of 21 squared, which is also 21. So fractions with the same denominator, 1 plus 4 equals to 5 plus 16, that's the square root of 21 over 21, which is the square root of 1, which equals to 1. So the reason why we are taking the magnitude is to make sure we get a 1 when we get the magnitude of the derivative of the new parameterized, of the reparameterized function. But what is that having to do with our purpose? Well, let's have a look at the theorem on the next page. So, if S is the arc length parameter for R, then the magnitude of R prime of S is always equal to 1. Furthermore, if T is any parameter for the vector valued function R such that the derivative of the velocity, the magnitude of the velocity, if that equals to 1, then T can also be the arc length parameter. That means I can simply change my variable T with the variable S without finding an expression to change the variable T to variable S. So let's have a look at a couple of examples to make more sense about this. Well, here, determine whether the parameter used in the vector function is arc length. So we're given a vector valued function. So in a way, we're going to make a test to determine whether I can simply change S without doing anything, without finding the arc length function. Can we do that? In a way, I mean, think of a test like those you did in calculus too, a test for convergence or divergence, for instance. So you will do a process. If you get this result, then converges. If you do this result, then diverges. Or in some tests, you get an inconclusive result. So in a way, we're doing something like that. We're making a test to determine whether we can simply change our variable T to a variable S or not. All right? So number 1, let's find the derivative R prime of T. That is the derivative of sine, which is cosine, that is 2 times cosine of T over 2. But I'm leaving a space for a mini chain rule, the derivative of T over 2, which is 1/2, comma, the derivative of cosine, that's negative 2 sine of T over 2. The derivative of T over 2, again, it's 1/2. All right, divide out, and that is cosine of T over 2, comma, negative sine of T over 2. Okay, so that is our derivative. So now we're ready to test this vector valued function to determine whether we can simply change the T with an S, or if we need to find a change of variables first before we can do that. All right, okay, so the magnitude of R prime of T, that is the square root of cosine of T over 2 quantity squared plus negative sine T over 2 quantity squared, that is the square root of cosine squared T over 2 plus sine squared t over 2. Well, cosine squared plus sine squared, is that equal to 1? I know it might look a little tricky because, or weird because of the angles, but as long as the angles are the same, t over 2, 70 million, t squared, cube, whatever, if you have the same angle for both terms, the identity holds. That is the square root of 1, which equals to 1. What does that mean then? And this is good. This means that I can simply go about reparameterizing r of t to r of s. So this same function parameterizes not only time, but also distance without making any changes to the variable. So r of s equals to 2 sine s over 2, comma, 2 cosine s over 2. All right? That's what it means. Alright, so what about letter B? Looks a little similar, but with a little catch right here. Well, number one, let's see if we can simply change from t to s like this, or if we need to do something else. So that means we make the test first. If the magnitude of the derivative of this given vector valued function equals to 1, then we're good to go. Okay, so r prime, that equals the derivative of cosine, which is negative sine. The derivative of sine, which is cosine. The derivative of t, which is 1. Let's find the magnitude. That equals the square root of negative sine t squared plus cosine t squared plus 1 squared. Okay, so that's going to give us the square root of sine squared plus cosine squared plus 1 squared, which equals to 1. And again, sine squared plus cosine squared equals to 1. 1 plus 1, isn't that equal to 2? That's the square root of 2. Oh, the magnitude of the derivative of this vector valued function is not equal to 1. So in this case, this is not the arc length parameter. Right? So it's not. One it is, the other one is not. However, even though it's not the arc length parameter, we can still find the arc length function. That's fine. All right? So, and that's example number 5 about. Well, then represent example 4b so that the parameter is the arc length. So even though right away it didn't give us the magnitude of the derivative of the function didn't give us a 1, we can still find that arc length parameter. How do we do that? Well, number one, represent this as an r of u, first of all. So that's where we need to make the change of variables. That is, r of u equals, that was cosine u, sine u, and u. Find the derivative, r prime of u, that equals negative sine u, cosine u, and 1. So what do we need to do? We need to find the arc length parameter, that is s equals the integral from 0 to t of the magnitude of r prime of u du. In other words, we're going to take the magnitude of the derivative, which is actually the same that we got before, you know? So, that is the integral from 0 to t of the square root of negative sine u, quantity squared, plus cosine u, quantity squared, plus 1 squared. All this madness here reduces to the square root of 2, right? We just have a different variable. That's all it is. So let me just go, du. Let me just integrate from 0 to t, the square root of 2, du. Okay, So this means s equals to square root of 2 times the integral from 0 to t of du. And in this case, I'm going to continue as an equation because I need to come up with the expression that actually reparameterizes. Okay, so that is s equals to the square root of 2 u from 0 to t. S equals the square root of 2 t minus 0, which is s equals to the square root of 2 t. And this is the expression or the equation, the relation, if you will, that we will use to change the variable t in terms of s. That means I need to solve for t that equals s over the square root of 2. So in order to turn the original vector valued function into arc that describes position after t seconds, or that rather as a unit of time, now into units of distance, all we do is reparameterize this as r of s and do cosine of s over the square root of 2 sine of s over the square root of 2 comma s over the square root of 2. So that is our vector valued function with a different parameter, but this time it will parameterize distance or arc length, not anymore time. I mean, if you want to verify this, of course, let's take the time just to verify. Let me take the derivative of this. Negative 1 over root of 2, all right? Sine s over root of 2, then 1 over root of 2, cosine, comma, 1 over root of 2. And then find the magnitude of this. And as a result, we should get a 1 to make sure we got it right. I mean, on an exam or something, you don't have to do this proof, if you will. All you need is to get up to the function. So let's see. That's negative 1 over root of 2 sine of s over the square root of 2 all squared plus 1 over root of 2 cosine of s over root of 2 squared plus 1 over root of 2 squared. So, okay, negative 1 over root of 2 squared, that's 1/2, right? That's 1/2 sine squared of s over root of 2 plus another 1/2 cosine squared s over root of 2 plus 1/2. Okay? Now, here is the thing. What is this sine squared plus cosine squared going to give us? Isn't that going to give us a 1 again? But that one having the same coefficient in common, that's going to give us 1 times 1/2, right? So all this madness here is 1/2. So 1/2. Oh, come on. So 1/2 plus another 1/2, what is that equal to? Isn't that equal to 1? Which is 1 as we're supposed to, right? So again, in summary, so again, vector valued functions have been seen as the position of an object at different times, but that's not the only parameter. We can reparameterize the situation instead of monitoring different times, monitoring different distances instead, and that is by changing the parameter to the arc length parameter. All right, so let's have a look. That's the end actually of section 14.4.